Hi folks, welcome to the Math 621B Chapter 11 Concept Roundup. In this video we're looking at counting techniques and at binomial expansion. As always, there's a downloadable copy of the notes in the video description as well as a review sheet for at least some of this material. Now, full disclosure, I don't always get to all of this chapter in class, so this video has 10 topics here that are stuff that I usually get to, and then number 11 and 12 are things that I don't always get to, but if you're interested in, it's certainly in the curriculum and it's in the book. Okay, we'll start off by looking at the fundamental counting principle. So the fundamental counting principle is a quick way to calculate all the possible outcomes in a situation with multiple parts. If we look at this setup here with the t-shirt that comes in small, medium, and large, and the colors red, blue, green, and white, and can have a crew neck or a v-neck, how many t-shirts are possible? Well, we could list them all out, right? We could say, oh, it could be small, medium, or it could be large. And if it's small, it could be red, green, blue, or white. Okay, and that could be the same way for the other one. And even if it's small and red, it could have a crew neck or v-neck. And getting them all to pop up like that, we can see that there are in fact 24 different options. But it's pretty painful to write them out, that there's small red crew, small red v, small green crew, etc. So the fundamental counting principle says the total number of outcomes is the number of choices for one item or parameter, so say the size, times the number of choices for another parameter, so maybe color, and so on. So here we also had crew versus v-neck. So essentially we had three things we got to choose. We got to choose sizes, we got to choose colors, and we got to choose the neck style. Okay. And what we're going to catalog is the number of choices. For sizes there were 3 choices. For colors, there were 4 choices. And for the next style, there were 2. And if you take 3, 4, and 2 and multiply them together, you get 24 total possibilities, or 24 possible shirt types. And that goes a lot faster. So let's look at a similar question here. We've got a group of 10 people, and 3 are to be arranged in a line. In how many ways can this be done? So think of places you have to make decisions here. There's going to be a first person in that line. There's going to be a second person out of those 3. And there'll be a third person. So you've got 10 people. Any one of those 10 could be your first person. Now for the second person, you've actually only got 9 to choose from now. Okay, because somebody is in the first place. For the third person, you've got only 8 to choose from because somebody's in the first and second place. And if we multiply these together, we get 720 possible different lineups. And that is clearly a lot faster than writing out all 720 of those possibilities. Now, if you've already been further in the chapter, you should note that this could also be done with permutations. And we're going to expand on this question and look at what could happen if we had more than 3 people. So this leads us to factorial notation. How many ways can you arrange 10 people in a line? Well, it's the same question. You got a first, a second, a third, and so on. And then there's a certain number of possibilities for each of them. So you've got 10 people to choose for your first person in line, which means there are 9 left for your second person, which means there are 8 left for your third, and so on. And that means we've got to multiply all of these things together. So we can do that in the calculator. Let's find out what 10 times 9 and so on makes. So 10 times 9 times 8. There, I've got it all typed in. You can't see it, but it does go along. 4, 3, 2, 1. Press enter or equals, we get 3.6 million. Wow, that's a lot. And it was kind of painful for us to put it in our calculator. There's a faster way for us to write this. So the easier notation above for the expression above is 10 factorial. It looks like 10 exclamation point. Your calculator should have a factorial button. Okay? And here's the definition of factorials. 1 factorial is just 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1, all the way down. So 10 factorial would be this thing that we just wrote up here. And on my calculator, I can go and say 10. And I have to go over and try and find it under probability on this Texas Instruments calculator. They're all a little different. But you can see that you can just type in 10 factorial, and it goes pretty quick. Generally, n factorial just means whatever the number n is, times n minus 1, so 1 less, times 1 less than that, times all the way down to 3, 2, 1. Some things we need to note here are that 0 factorial is defined as 1. And we only define factorials for natural numbers and 0. We don't deal with 0.5 factorial. It's not a thing for counting. There is a continuous curve called the gamma function that you could look into, but it is way beyond the scope of this course. So factorial is fairly straightforward for us to evaluate. If we want 5 factorial, I just go ahead and type in 5 factorial. Boom, it's 120. For the next one, it's asking us for 8 factorial over 6 factorial. Okay, so that is not the same as 8 over 6 and then do your factorial. It has to be 8 factorial divided by 6 factorial. And that gives us 56. Now here, there's another way we could think of this. 8 factorial means 8 times 7 times 6 the rest of the way down. That's 6 factorial means 6, 5, 4, 3, 2, 1. All over 6 factorial. These things can be divided out. They're equivalent. They're in factored form. Okay. So the whole expression just means 8 times 7. And you might say, okay, that's fine, but I can just do it on my calculator. The problem is that factorials get really big really fast. So if I try on my calculator to do 100 factorial over 98 factorial, I think it's going to be unhappy with me. Let's see. Unless my calculator's super fancy, which it is not. It says overflow. Okay, that means that the numbers are too big for the calculator. And that's pretty big. 10 to the 99 is how big the calculator goes. So 100 factorial is too big, but we can still do this question. 100 factorial means 100 times 99 times 98 the rest of the way down over 98 factorial. Oh, look, so the whole thing just means 100 times 99, or 9,900. But since your calculator tries to do the top and bottom separately, it can't think that way. If we try and look at it abstractly, n factorial over n minus 2 factorial means, okay, n factorial will be n by n minus 1 by n minus 2 by n minus 3 and so on. And we just have to decide where we want to stop writing all the individual terms. And I would say it's right here. Because this way, n minus 2 factorials divide out. And we're left with just n by n minus 1, or n squared minus n. So we can do it in abstract settings, and we can do it for specific numbers. That leads us into permutations. So permutations are arrangements of objects where the order of the objects matters. The number of possible arrangements of R objects from a group of n non-identical objects, and we'll deal with identical objects closer to the end of the video, is given by this formula right here. N factorial over n minus r factorial. So if we redo question 2 that says in how many ways can you line up 3 people from a group of 10? That means we have 10 non-identical objects, or people, and we're going to take 3 of them. That would be our R. So I should be able to figure this out as 10 factorial over 10 minus 3 factorial. Okay? And I can do that in my calculator. I can also do it with my brain and say, oh, it means 10 times 9 times 8 times 7 factorial, all the rest of the way down. And I'm going to get the exact same answer that I got when we did this in question 2, 720. Now, the notation for when you find the number of arrangements of R objects from a group of n identical, non-identical objects, is this, NPR. And this can be evaluated with this formula that's up here. So that n factorial formula, that is the NPR formula, where NPR means the number of possible permutations. Or there's a button on your calculator. Okay. So if I were to do this question that was up top here again, I could just say it's 10p3. Or sometimes we think of it as 10, and we pick 3. 10 pick 3. Okay. On my calculator, all I do is type in 10, and I go and find my NPR button, which happens to be under probability on this calculator. I go 10 pick 3. Boom, 720. That easy. And most of the time, you're going to be able to use your calculator, so it goes pretty fast. Otherwise, maybe use either fundamental counting principle or the formula. So from a set of 11 different books, in how many ways can you arrange 6 of them on a shelf? Ask yourself here, does order matter? Yeah, for arrangements, order matters. Having one book and another switch places would be a different arrangement. So this is a permutation. And there are 11 objects, and we're taking 6 of them. In other words, it's 11 P6, or 11 pick 6. Let's find out how big that is. Whoa! Gets pretty big, pretty fast. 332,640. Now, one thing that you really need to notice at this point is that we've got this idea wrong from our combination lockers. Since order matters in a permutation, your so-called combination lock is really a permutation lock. Okay? If you have the combination 10, 20, 30, and you put in 30, 10, 20, it's not going to open. The order of the objects matters in your code lock, so it's really a permutation lock. That might lead us to ask, okay, well then, what is a combination? So mathematically, we say a combination is a selection of objects where the order of the objects does not matter. So that's different from a permutation. In a permutation, it matters, the order. In a combination, it does not matter. The notation for the number of ways to select R objects from a group of n is NCR. So no surprises here. Combination is going to use a C. Permutation uses a P. Or this is more common international notation. And there's a formula for calculating the number of possible selections. And it's similar to the last one, but it's got this extra R factorial here. Your calculator is going to have an NCR button as well. So let's take an example that's similar to one we've worked with. From a group of 10 students, 3 are to be selected to go on a field trip. How many different selections are possible? Okay, so think about this. How is this different from the lineup? In the lineup, if you have Alice, Bob, Carl, that's a different order than Bob, Alice, Carl. But if all you care about is who's in the group, or who the team is, Alice, Bob, Carl, and Carl, Bob, Alice, and all those different ways of arranging them, all mean the same thing. That means generally there are going to be fewer combinations than there are permutations. Okay? So this is a case where order doesn't matter. We're just selecting 3 people. It doesn't matter which order they're selected in. There are 10 of them. That's our n. We're taking 3. That's our r. It would be 10C3, or sometimes we say 10 choose 3, just to help us remember that that's how many we're taking. Okay. So that would be 10 factorial over r, that's our 3, so 3 factorial, and n minus r factorial, so that's 10 minus 3 factorial. Okay. Or 10 factorial over 3 factorial, 7 factorial. Now, if I show this algebraically, let's see what's going to happen here. I'm going to have 10 times 8 times 9 times 7 all the way down, okay, times 3 factorial, 7 factorial. So those 7 factorials can go. I know that this is 720. I also know that the bottom is 3 times 2 times 1 because it's 3 factorial. So you can see right there how the number of possibilities goes down for the combinations. If it had been a permutation, we'd have 720. Here it's going to be 720 divided by 6, or just 120. Now, if you don't want to see any of that in motion, you just go to your calculator and say, all right, it's 10. I go over and find my NCR button, 10C3, or 10 choose 3, and it tells me 120. Let's take a look at one other one here. A restaurant offers 14 different pizza toppings. How many different 5-topping pizzas are possible? So ask yourself, does order matter in pizza toppings? You might say, well, I like to have my pepperoni on the bottom or pepperoni on the top. Sure, but when you call up an order, you don't specify what sequence they're allowed to put the toppings on. Maybe there's a general one that they use, but here order does not matter. You don't specify. So there are 14 objects. You're taking 5 of them at a time. It's a combination because order doesn't matter. And we just go 14C5. I head to my calculator to evaluate that. And if I don't have to, I'm not going to use the formula. There we go. There are 2,002 different 5-topping pizzas. Now, one of the places this gets dicey is just in telling the difference between permutation and combination questions. So in permutations, order matters. Ask yourself, does the order of the objects matter? Some possible keywords are arrange or line up, but they're not guarantees. Combination, order doesn't matter. Okay. So ask yourself, does the order of the objects in question make a difference? Possible keywords are select or card hands. So if you have a card hand, the order that you hold them doesn't make a difference. Whether it's you have the Jack, King, and Queen of Hearts, or you have the Queen, King, and Jack of Hearts. Same thing. So order wouldn't matter typically in card hands. From a group of 12 different Star Wars action figures, in how many ways can you line 5 up on a shelf? So ask yourself, in a lineup, does the order matter? For sure, generally you'd prefer to be at the start of a lineup than at the end, depending on the lineup. So this is a permutation question. Okay. N is 12, R is 5, it's 12p5, whatever that is. So we'll take a second here, figure it out. $95,040. Now, suppose instead you're just going to put 5 of them in your backpack. Does it matter which order you throw them in? No. They're just going in your backpack. So, this is a combination. Order of the objects does not matter. So this would be 12C5. And again, we can run that through on the calculator and see what we get. There we go, 792. Far fewer possibilities if order doesn't matter. Let's try another one. A band knows 20 songs. and they have to make a 12-song set list. In how many ways can this be done? So in a set list, does order matter? Generally, if you've ever been to a gig where somebody plays the ballads right off the top, it makes a difference to hear a ballad as the first song compared to a fast song. The order in a set list matters. So order matters. So it's a permutation. Okay. There are 20 objects, and we're going to pick 12 of them. And we'll just figure out how big that is. Pick 12. Whoa. 6.03. And then mine says E13. That means times 10 to the 13th. And sometimes we find it hard to figure out, well, how big does that mean? That means that there are roughly 60 trillion different 12-song set lists that they can make just from 20 songs. Numbers get big fast. Lastly, how many 5-card hands exist using only hearts? So a deck of standard cards is made up of 52 cards. Half of them are red, half are black. So 26 red ones. Of the red ones, half of them are hearts, half of them are diamonds. So there are 13 hearts. Now, does the order you hold them in your hand matter? No, it does not. So this is a combination. And you're going to choose 5 of them. Let's figure out how big that is. $1,287. Okay. So now we can tell the difference between a permutation and combination question by asking ourselves whether order matters. Let's move on to some more involved counting questions. So they might have multiple parts. They might use the word and or at least. If you see the word and, like 3 girls and 5 boys, or 2 books and 7 DVDs, that typically means that you're going to multiply your results. If you see the word or, like 3 books or 5 DVDs, typically you add your results. And if you see the word at least, it implies that there are multiple cases to investigate. And so do the words at most, or less than, or more than. So let's figure out this first one. In how many ways can you line up 5 or 6 people from a group of 10? Now it's starting to all come together here. It says line up. Does order matter? Yeah, order matters. So that means it's a permutation. Yay! And usually what I do is I'll write it out in words. That I need 5 people or 6 people. That's the scenario. Now I need to translate that into math. So I've got 10 people, and I can pick 5 people. Or I could pick 6 people. I'm dealing with these separately. And the word or means I add my results. Now, rather than going to the calculator every time, I'm just going to write down the values that would come out here. So we get 10p5 is 30,240. 10p6 is 151,200. And we need to add those two things together. So that's going to give us 181,440. And you can pause the video and try that yourself if you like. A team needs to have 3 girls and 2 boys. How many teams can be formed from a group of 8 girls and 6 boys? A team. Let's see. Does it matter on a team the order that I pick the people? Like, is the team Alice and Bob the same as the team Bob and Alice? Unless we're talking about specific jobs for people, the answer would be yes. A team would typically imply combinations. That order is not important. The order of selection is not important. So again, I'm going to write this out in words. The setup is that there need to be 3 girls and 2 boys. Now for the girls, I have 8 to choose from, and I'm going to choose 3. Again, I'm using C because it's a combination question, because order doesn't matter. For the boys, I have 6 to choose from, and I'll take 2. And means I multiply those results. So again, you can pause and do the math if you like, but this means 56 times 15, or a total of 840. Sometimes the AND questions are a bit sneaky. So here it says, how many 4-card hands have exactly 3 diamonds? Okay, again, I need to write out what this looks like. So they're card hands. The order that they're held doesn't matter. This is a combination question. But there are 4 cards. I know that 3 of them are diamonds. There needs to be another card. So this really means 3 diamonds and 1 non-diamond. And I think about my deck of cards. There are 13 diamonds, because half the cards are red, and half those red cards are diamonds. And I'm going to choose 3 of them. Now, how many non-diamonds are there? The other 39 cards out of the 52 in the deck are not diamonds. So that's going to be 39, and I'll choose one of those. And I need to multiply these two things together. If we go to the calculator, we'll get this is 286. The number of ways that you can choose one card from 39 is 39. 39C1 is going to be just 39. Multiply them together, and we get 11,154. Now lastly, let's look at this one, where we have 4 card hands that have at least 3 diamonds. At least means that there might be cases, or there likely are. So case 1, if there are at least 3 diamonds, means that there are 3 diamonds and 1 non-diamond. We just did this. Okay? And we know that that means 13C3 times 39C1. And the result's going to be 11,154. But that's not the only thing that could happen if there are at least 3 diamonds. There could also be case 2, where you just have 4 diamonds. That is a terrible looking diamond. Let's try that again. Perfect. Okay. And there would be 0 non-diamonds, so I don't even need to write it out. How many ways can I choose 4 diamonds? Well, 13C4. And it turns out that that is 715. And the question is, what do I do with these numbers? Well, let's think back to it. You've either got 3 diamonds and 1 non-diamond, or you've got 4 diamonds. That means we're going to take these numbers and we're going to add them up. Okay. So for a final answer of 11,869. So recap, and means multiply, or means add, at least means there are cases. That's as far as we're going to go into the counting methods right now, but at the end of the video we'll deal with some more abstract ones, algebraic ones, and some equations, as well as some permutations with repetitions. Where we'll go next, though, is to Pascal's triangle, which in your textbook is 11.3. And it starts to deal with something called binomial expansion. So here's the thing. If I took all of these different combinations and I actually evaluated them, it turns out 0C0 would be 1. And 1C0 is 1, and 1C1 is 1, and 2C0 is 1, 2C1 is 2. And I'm just going to write these all in. And now I'm going to move away the combinations themselves. There we go. I get this little triangle with those values. And if you think back to when this mathematics would have been developed, it would have predated calculators by a long shot. So if you wanted to know what 15 choose 7 is, well, you didn't have a calculator to help you out. And Pascal's triangle is one way for us to organize the combinations. Now, full disclosure, the triangle is known way before Pascal's time. Pascal gets his name on it for algebraic and kind of probability purposes because he brought those applications in. So some things to notice on Pascal's triangle. The outer numbers are all 1. All these numbers are coming from combinations. Each row has one more member than the previous row. So the first row just has a 1. The next row has 2 members. It has 1, 1. The next one is 1, 2, 1, so it has 3 members, and so on. So if I needed to make the next row, I'd need some sort of pattern. Here's what I'd know. It starts with a 1 on the outsides. Okay, the outer numbers are 1. And I know that it's going to have one more number than the row before. So the row before had 5 elements. This one's going to have 6. The inner numbers come from the sum of the 2 above them. So if I looked at this 2 right here, it comes from 1 plus 1. Or if I wanted to figure out where this 4 came from, it comes from 1 plus 3. Where does this 6 come from? 3 plus 3. That gives us an easy way to generate the next row. Okay? So the next term is going to be 1 plus 4 gives us 5 right here. 4 plus 6 gives us 10. We get 10 again. The triangle itself is symmetrical. So students often ask, do I have to memorize the triangle? No, you just have to know how to generate it. Once you get the idea that it's 1s on the outside, that it makes a triangular shape, and that the inner numbers are just the sum of the 2 above it, then it's fairly straightforward. So if I were to do the next row, it would be 1, and then my next number would be 1 plus 5. Oh, that's 6. 5 plus 10 is 15. 10 plus 10 is 20, and so on. And then the next row is easy to make. Okay? And each of these numbers actually have meaning. So this number right here, that would be 6C0. This number right here, that would be 6C2. This number right here, that's 6C5, and so on. So it's a cute little calculator for combinations. It has a ton of other patterns in it. You could get lost for a week looking for them, and it's kind of a fun thing to do. But not something we have time for right now. Okay, so why do we care about this? Well, if we expand some binomials, if I take a plus b to the power of 1, that's just a plus b. If I have a plus b to the power of 2, I know that's a plus b times a plus b. And here's what it gives me. A squared plus 2ab plus b squared. If I had a plus b all cubed, that's a pain for us to figure out. We'd have to go a plus b times a plus b times a plus b. And I'm really hoping that you'll take my word for it that this is what we get. A cubed plus 3a squared b plus 3a b squared plus b cubed. And a plus b all to the 4 would be even worse. So I'm going to let you know this is the result that you would get. But if we did it by foiling it out and foiling it out again, or using distributive property a whole bunch of times, chances are we're going to make a mistake. So here's the result of a plus b to the 4. Now those numbers should look a little bit familiar. Notice that there's a secret 1 coefficient in front of all of these. Ooh, that makes us think of Pascal's triangle. Pascal's triangle looked like this. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4. I'm running out of space, but there's a 1 there. Doesn't look very triangular anymore. Those coefficients are the same as we've got in our binomial expansions. So what we want to notice about binomial expansion is a few things. When we expand a binomial, the coefficients, those initial coefficients, come from Pascal's triangle. When we look at an expansion, the powers of a, they always start high. Like if it's a power of 3 on the binomial, it starts with an a cubed. If it's a power of 4 on the binomial, it starts with an a to the 4. And then, as we go through the expansion, you can see here it's a to the 4, then a to the 3, then a to the 2, then a, and then it disappears in the last term because it's a to the 0, which would just be the number 1. By contrast, b is not even there in its first term, and that's because it's really b to the 0 here. And then it goes b to the 1, so it really makes its first appearance in the second term of the expansion. And then b to the 2 and b to the 3, and it ends up with a high power on b. And one other thing we might want to note is that the expansion has one more term than the power on the binomial. So when we had a plus b to the power of 1 here, there were 2 terms in the expansion. When we had to the power of 2, there were 3 terms in the expansion. Okay? When we had to the power of 4, there were 5 terms in the expansion. And this whole pattern is going to let us expand binomials efficiently and quickly. Now, it turns out that that has a big application in probability. So it starts out being something that looks kind of abstract and useless, but it's not. Okay, before we go there, I just want to show you this cute little tool that I like to use called Pascal's Headless Triangle. And it's really just Pascal's triangle starting with this row, with the 1, 1, without the top row. So it goes 1, 1, and then the next row is going to be 1. 1 plus 1 makes 2. 1, 2, 1. And we just keep going. Okay, so extra number in the next row. 1 plus 2 makes 3. 2 plus 1 makes 3. 1 on the end. 1 plus 3 makes 4. 3 plus 3 makes 6. 3 plus 1 makes 4. And so on. And I think Pascal's headless triangle makes some of your binomial expansion a little bit easier because that pesky first row can get in the way. But on Pascal's real triangle, this is what's expected in textbooks, that you would have a 1 on the top there. Okay, so here's my sales pitch for Pascal's headless triangle. First of all, I'm going to write it out over here. So I'm going to have 1, 1, then 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. I want to expand a plus b to the power of 4. Here's what I do. I write the coefficients from the 4th row of Pascal's headless triangle. Okay? So that would be this one right here. If you're using Pascal's real triangle, that's the 5th row. So it's 1, 4, 6, 4, 1. Okay? And I'm going to put a plus in between them. And here's what's going to happen. We said that the powers of a started out high. So we're going to have a to the power of 4. And its powers go down. And I always write it in this order. So its powers go down. It's a to the 1 now. Then it's going to be a to the 0. So it'll disappear. B, on the other hand, it starts at a power of 0 in the first term, so we don't see it at all. In the second term, it makes its appearance. So b to the 1. Then b to the 2. Then b to the 3. Then b to the 4. Now I can just figure out what these mean. So that means 1 times a to the 4. 4a cubed b. 6a squared b squared. Plus 4a b cubed. Plus 1 b to the 4. Those 1s are kind of weird, so let's just write it out this way. A to the 4 plus 4a cubed b plus 6a squared b squared plus 4a b cubed plus b to the 4. You might say, well, you just told us that in the last page. Yeah, but we want to set the groundwork here so that we can expand different binomials. Okay, so that's how it works with a plus b. If you're not convinced, you can write out a plus b 4 times and FOIL away and hope not to make any mistakes. And you should end up with this result. It's going to be the same process if we have 3x minus 2 to the 4. We're going to go to the fourth row. Okay. And I'm going to write down those coefficients in the fourth row. And it does take a little bit of space. It takes a little bit of time, but way less time than foiling it out a bunch of times. Ask yourself, what's different here? Instead of a, there's this term, 3x. That's kind of our a-type term. So it's going to start with a high power. We're going to have 3x to the 4. Compare that to what's above. We had a to the 4. So same thing, just instead of a, we have 3x. And its powers go down. 3x to the 3, 3x to the 2, 3x to the 1, and it's gone for the last term. The negative 2, that's going to be our b. It's not going to show up in the first term. And then we're going to have negative 2 to the 1, negative 2 to the 2, negative 2 to the 3, and negative 2 to the 4. That is the expansion. It's just not put in pretty form. Okay? So notice, like these three terms here, they need to have their exponents dealt with, and they need to be multiplied together. But they're ready to go. I really recommend that you do this in 2 more steps. So the first of those steps is just apply the exponents. 3 to the 4 is 81, x to the 4. Okay, remember to apply that power of 4 to your 3. The next one, we're going to have 4 times 3 cubed. Oh yeah, that's 27. X cubed times negative 2. The next one, we'll have 6 times 9x squared times 4. The next one, we'll have 4 times 3x times negative 8. And lastly, we'll have 1 times 16. And here, in your final step, actually put it in a nice form. So 1 times 81x to the 4 is 81x to the 4. Next term, 4 times 27, that's 108, times negative 2, that would be negative 216, x cubed. There's your next term in the expansion. The next one will have 9 times 6, that's 54, times 4, so that is another 216. This time it's positive. The next one, 4 times 3 times negative 8, so that's 12 times negative 8, or negative 96x. And finally, 1 times 16 is just 16. When you're done here, you should have no like terms to collect. This is the expansion. So there is a full expansion of a binomial. And again, lots of applications in probability that we can look at some other time. Okay, the last thing on binomial expansion is that sometimes you'll only want a specific term in a binomial expansion, not the full expansion. And again, we've got these applications in probability where this might come up. So I'll just give you a quick aside. It might come up if you know that the percentage of free throws that somebody makes is 70%, and you want to know what the likelihood is that they'll make 12 out of their next 17 free throws. This kind of math comes into play. So if you want a specific term in a binomial expansion, you can use a formula like this, where n is the power on the binomial, a is the first term in the binomial, b is the second term, and r is the tricky one. It's one less than the desired term number. So in this example 17, if I want the 7th term in the expansion of 2x plus 1 over x all to the 8, that 8 is going to be my n. Okay. This 2x, that's my a. 1 over x, that's my b. And we're looking for the 7th term, so r is 1 less. r is 6. Let's use that formula that's above. So it would say NCR, so 8C6 of a, that's 2x, to the power of n minus r. So that's 8 minus 6. b, which is 1 over x, to the power of r, which is 6. Now, we can work this out. 8c6, you can go to your calculator. That's 28. 2x to the 8 minus 6. Make sure you do that 8 minus 6 in your head. That's just 2. So 2x all squared would make 4x squared. And 1 over x to the 6 would be 1 to the 6, which is 1 over x to the 6. Okay. Put that all together. 28 times 4 makes 112 over x to the 4. You might say, well, that's a little bit painful. Yeah, but compared to doing the full expansion of that whole thing, which would need the 8th row of Pascal's headless triangle, this is way, way slicker. And let's try something similar here. We want to find the middle term in the expansion of 2x minus 3 to the 6. Okay, so stuff we know. We know that 6 is n, and that 2x is going to be a, and that negative 3 is going to be b. But I don't even know which term number I want. So you have to remember that if we've got a power of 6, there are going to be 7 terms in the expansion. Okay. And if you have 7 objects in a row, the middle one is the 4th term. So if there are 7 terms in this expansion, the middle one's the 4th term. And r is 1 less than the term number we want. So r is 3. Let's set this up. So it was NCR. So that's 6c3, a to the power of n minus r, b to the power of r. Okay. We worked that whole thing out. 6c3 is 20. This is 2x to the 3, so that's 8x cubed. And negative 3 to the 3 would be negative 27. And now I just have to multiply those together. And the most common question I'll get on this is, what do you do about the x's? Well, your calculator deals with the numbers. You folks deal with the x's. So now we know the coefficient is negative 4320. X cubed. There's nothing to solve. That's the term. And again, it's shorter to find a single term, if all you need is a single term, than to do the full expansion. That gets us to the end of where I usually get to in class. But here's the other stuff that's in the chapter if you're interested. So let's say we want the number of ways that you can arrange something that has identical objects. So if you have 10 different people in a line, it's no problem. But if you had all the letters in the word book, you've got identical O's. I can't tell them apart. And when we did permutations earlier, we said we needed non-identical objects. Here's what happens when you have some identical objects. So these are all the ways I can think of to rearrange the letters in the word book. We've got book, we've got boko, baku, koob, kobo, kaboo, ubg, ukb, okab, obak, okbo, and obko. If you find another one, put it in the comments below. Here's the thing. We found 12, but if I went to my calculator and figured out 4p4, it would tell me 24. So that's weird. We have fewer than we expected. Okay, and the reason I go 4p4 is that there are 4 objects, and we're selecting 4 of them. When there are identical objects, the number of possible arrangements decreases. And that's because you can't tell the difference between whether this was O1 or the second O that went here. They're the same. As a rule, the number of permutations of n objects where there are A alike of one kind, and B alike of another kind, and C alike of another kind, okay, so those don't have to be the letters A, B, and C, just how many alike of one kind, is n factorial over A factorial, B factorial, C factorial, etc. So if we look at that on the word book, there are 4 letters, so that's going to be our n. So we go 4 factorial, but there are 2 identical O's. And if I work that out, I know that 4 factorial is 4 times 3 times 2 times 1, so that's 24. And 2 factorial is 2. That gives us our 12 possibilities. Let's take a look in one of the best words to look at this in. How many ways are there to arrange all the letters in the word Mississippi? So if I were to do that just with permutations and say, okay, let's see, first of all, how many letters are in this word? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 letters. If I checked it out just with regular permutations, I went 11, P, 11. That's a lot of possibilities. 39 million. Almost 40 million. But the thing to notice is that there are 4 identical I's. And there are 4 identical S's. And there are even 2 identical P's as well. Spelling. There we go. Identical. So if we set this up, we'd say there are 11 objects, but 4 alike of one kind, and 4 alike of another kind, and 2 alike of another kind. And I'll work that out, and it better give me a lower number. Otherwise, something is very weird. Now, maybe you have a fancy calculator where you can do kind of a numerator over denominator thing. That's great. Otherwise, if you're just putting it in a regular kind of 2-line calculator, put brackets around the bottom so that it groups them together well. 4 factorial and 2 factorial. Now, you should know that 2 factorial is just 2. So that might save you a second here. Okay. Let's see what it gives us. 34,650. Wow, that is a big, big difference from 40 million down to 34,000. So that's how we deal with some of these permutation questions with identical objects, and that's actually where the combination formula comes from. Lastly, we're going to look at equations and expressions that involve factorials. So the thing to remember here is that n factorial means n by 1 less times 1 less than that, so on, all the way down to 3 times 2 times 1. So if I want to solve np2 equals 42, one thing I might want to recall is the NPR formula. And that's n factorial over n minus r factorial. Now here we've got np2. We have np2. So that would be n factorial over n minus 2 factorial. And that can simplify. N factorial means n times n minus 1 times n minus 2 the rest of the way down. But hold on, the bottom is already just n minus 2 the rest of the way down. So really this whole setup here of np2 can be rewritten as n times n minus 1. So we might say, oh, wow, since I was able to do some simplification, since np2 equals n by n minus 1, we're really solving this. It says np2 equals 42, so that means n by n minus 1 equals 42. And that looks a lot like a quadratic because it's a quadratic. That's why it looks a lot like a quadratic. Okay, so n squared minus n equals 42, or n squared minus n minus 42 equals 0. We make one side 0 because it's a quadratic. We factor it. We get n minus 7 and n plus 6, numbers that multiply to negative 42 and add to negative 1. That's going to give us answers of n equals 7 and n equals -6. Now, we don't define factorials for negative numbers for these counting questions. So n can't be -6, but it could be 7. Let's check. Does 7p2 equal 42? Okay. And hopefully in the time it took me to write that down, you went and checked and said, oh yeah. Sure does. Great. So n equals 7 is our answer. Now, if you have your calculator, it's probably just as fast to guess and test numbers here. There are only so many you can go through before you're going to run into the answer. So the algebraic approach doesn't necessarily help that much in something that's this straightforward. One other thing to notice is that factorization is possible. So if we have 5 factorial plus 4 factorial, 5 factorial means 5 times 4 times 3 times 2 times 1. Okay, 4 factorial means 4 times 3 times 2 times 1. Look at the common factors there. There's 4, 3, 2, and 1. In other words, 4 factorial is a common factor. It's here and it's here. And what would it leave us with? It would leave us with the 5. And of course, if you factor everything out of an expression, you're left with a 1. So we get 4 factorial times 5 plus 1, or 4 factorial times 6. In a similar way, n factorial plus n minus 1 factorial. Well, n factorial means n times n minus 1 the rest of the way down. And this is already n minus 1 the rest of the way down. Ooh, look what we've got. Common factors of n minus 1 factorial. That's a common factor. What does it leave us with? It leaves us with an n and this secret coefficient here of 1. I'll rewrite that in black just so it looks normal. So that's a way that we could simplify or rewrite that expression in factored form. Okay, so similarly, we can do some nifty simplification. If I have this thing up here, n factorial plus n minus 1 factorial, that's literally the factorization we just did. But I'll show the method again. That means the top looks like this. The bottom is similar. It's got n factorial, which is n by n minus 1 factorial, minus n minus 1 factorial. So on both top and bottom, you have n minus 1 factorial as a common factor. What does it leave us with? Well, on top, it would be n plus 1. On the bottom, we'd have n minus 1 factorial as a common factor, and it would leave us with n minus 1. Okay. And that means we can divide these out. So this whole messy expression simplifies to something that doesn't involve factorials at all. Now, you cannot simplify that any further. You cannot divide out those n's. That would be illegal in math. I hope that you found this helpful. Sorry it ran a little on the long side, but again, we won't necessarily get to everything in class that's on this video. Good luck with your studying, and again, there's a practice sheet in the video description below. Take care.